Abstraction. This is a joint work with Jeremy Yallop from University of Cambridge on the subject that we call causal commutative arrows. But before we dive into the details of this arrow stuff, let me first give you a motivation. So the question we're trying to answer is, can normalization be used as an optimization technique? At first it sounds plausible because normalization as we know it, it preserves semantics. And it can also be effective when some conditions are met. First of all, it has to terminate in a reasonable kind of sense. And it should lead to some simpler, somewhat simpler program as a result. By simpler, what I mean is it can be simpler in the program structure, or it can be some simpler in the calculation, computation kind of sense. So by some metrics is simpler. And if it can enable some other optimizations, then it'll be all the better. But there are also some catches. First of all, not every program is strongly normalizing. And to enforce this normalization property can be overly restrictive because the program you're interested in may not have this property. And also sharing is hard to preserve, as we know it in normalizing lambda terms. It's very hard to avoid duplication of functions and of computation, and so it may not lead to simpler results. And lastly, there's a question of whether this normalization should be done at static or dynamic time, whether it's compile time or runtime. So this last question is actually the focus of this talk. And now let's review some basic concepts about arrows if you're not familiar with it. So John Hughes first introduced the concept of arrows as a generalization of monads. So the arrow type here, ARR, takes two type variables, A and B. We can think of it as some kind of computation mapping from something of type A to something of type B. So ARR is a lifting operation, lifting the pure computation at the normal term level to the arrow level becomes a pure arrow. So this can be depicted in the diagram here. So this corresponds to the lifting of function f. And then we have sequential composition. We can compose two arrows together by connecting the outputs to the inputs. And also we can do parallel composition. This is done by introducing a first combinator which lifts an arrow f to apply to the first argument. And symmetrically, second f can be defined in terms of first f, and if we sequentially compose first f and second f, we have parallel composition. Notice here the parallel composition can be done in one way or another. If we switch f and g, it may result in different arrows because arrows can be effective. They can have effects, side effects. So this order is important in the general arrow setting. And Ross Patterson also introduced arrow loop class, in which he introduced a loop combinator. Basically, you connect the output of the second output back to the second input, which forms a kind of recursion at the value level. So notice this is only a recursion at the value level. The arrow itself is not recursively defined. So arrows comes with a set of algebraic laws, and so does arrow loop. I won't go into the details, but these laws are critical to this work. Let me first give you an example of the normalization of arrows in terms of data flow. So without showing you the actual code, I instead present you the arrow diagram. So I won't go into the detail of this program, but it suffices to notice that there are some pure computation simplified by the circles, and there are some stateful computation, and all the wires are connected together except the input. So the input is ignored. The computation is entirely based on its internal states, which are introduced by the two square boxes. It turns out this computation can be normalized into the second diagram. So in this diagram, you can notice that all the pure computations, they are grouped together, and all the stateful computations, they're grouped together. So not every arrow program can be normalized. So only a subset that we are interested in. This is the subset that we call causal commutative arrows. Well, if you squint hard enough, you can tell the graphs, they are isomorphic to each other. So CCA, in short, is a more restricted arrow with an addition of init combinator we introduced in the arrow init class. Usually this can be thought of as a delay operator in electronic circuits or in data flow. But here we call it init. We just to emphasize the nature of initial value rather than the delay, which is very operational. And there are, in addition, there are two additional arrow laws we introduced together with this arrow init class. So the first states that, well, the parallel composition, just now I mentioned, for general arrows, they do matter, but for CCA, they do not matter. They're equivalent. And if you combine two init arrows together in parallel, is equivalent to init of a product of the initial value. So it turns out CCAs can be normalized. There is a normal form that can be proved by algebraic laws. It's either a pure arrow or some arrow of this loop D form. So this on the right hand side of this loop D, you can notice that each of the arrow combinators, they are used exactly once. There is our pure arrow, there's sequential composition, and there's second that symbolizes the parallel composition, and there's stateful arrow we introduce with arrow init, and on the outside there's the loop. So this kind of normal form does simplify the overall compositional structure of your arrow program. And it actually leads to some very good results as previously reported. But before showing you that, I'll first show you a concrete implementation of the arrow init or the CCA. So this is data flow or stream computation where we define a concrete data type called SF that symbolizes stream transformer from an input stream of type A to the output stream of type B. So this is implemented as basically is a function that takes the input, gives you the output together with the continuation for the next time step. And we can declare instances of SF in arrow class, in arrow loop class, and arrow init class. I won't go into detail, but for just one example of the pure arrow, right? Pure arrow definition, you can see here, this G is defined as taking the input X, applying the pure function to the X, and the continuation is G itself. So it's kind of recursive. Notice this SF data type is recursively defined. The important thing is that we can turn this stream transformer into a computation over input stream, that we just reuse the list type as the stream type, and we can define this run function that gives you the output list. And furthermore, we can, if the input list is constant units, then we can define a different unfolding function that samples a particular position into the output and gives you just the output at that position. So the previous result of this CCA work gives orders of magnitude speed up if you normalize your arrows, which sounds pretty good. So this is a comparison of the SF arrows that we saw in the last slides. And if we normalize it to the normal form and still in the SF arrow, we already can obtain some speed up. And furthermore, if we take out the states and the transition function in the normal form, we get even more speed up. All this looks pretty nice, but why is everyone not using it? Kind of sad. And this is not even used by Utopia, which is the music and sound synthesis framework from the same research group that came out this CCA work. So why? Well, there are some limitations in our implementation. The initial CCA implementation was using template Haskell because, first of all, normalization is a syntactic property. You can transform the programs entirely in a syntactic form to get the normal form. So it's convenient to implement this at the meta level, and at meta level we can guarantee that the result normal form is fed to the compiler, and then we can get the all the benefit from the normalization. And we implement it in template Haskell, which is less work than the full-blown preprocessor. But this template Haskell-based static normalization is kind of restricted because CCA applies only to first-order arrows, meaning that it can only handle arrows that does not carry another arrow in the wire. So it doesn't return an arrow in the output, which is required to model reactivity in FRP. But because this implementation, it cannot easily work with high-order arrows. This can be explained by, some example here. So if we define some function f that takes argument x, and then here we have some template Haskell stuff, and in which you use x, right? But in order for this to work at the compile time, x has to be in the lift class. So it means we have to be able to lift the value of x from the value level to the meta level so that we can compile it statically. This is sometimes overly restrictive. For example, if x is some kind of data structure, then you have to define your own instance of a lift class. What if x is a function, right? If it's a global function, template Haskell handles it, but if it's some local function you generate, then it's pretty hard. It's pretty hard to work around. It can be worked around if you try hard enough, but it's difficult. And then in order to normalize something, we splice the normalized result back into our program, but this G has to be defined in a different module. So all this is extra hassle, and eventually there's no sizable, we didn't even try to implement a sizable program with this implementation. So maybe it's not as effective as we had thought for real applications. Perhaps that's why nobody was really using it. So how about we try dynamic normalization instead of doing it statically? This actually has been tried before. So Jeremy sent me his implementation back in 2009 when he got a hold of our draft paper. And to which I replied, well, your program looks nice, but it's not really performant. Do you have any solution to that? And turns out we don't. I even discussed this in my PhD thesis, a variant of this implementation, saying, well, because you produce the normal form at runtime, how can you get hold of the state and transition function embedded in this normal form and give it to GHC to normalize, to optimize? So which sounds like kind of impossible, right? And indeed, we didn't, no matter what kind of program we try, we didn't get the same speed up as the static implementation. So that's the background of my talk. I'm here to tell you some good news. Yeah, we can do the normalization in runtime now and get good performance. So how we do this is, well, there's some technique called normalization by construction. This is not our technique, but we didn't really know who first invented this, but, well, we go into some details of this. We first define normal form as a data type in the program, and this data type, we use GADT for this because this C is actually not escaping from the type definition. But GADT is not strictly necessary, and you can use existential types. So AR represent the pure function as a normal form, and loopd represent the loopd normal form as we saw just now. It has a state, it has the transition function, and that gives you the normal form. And secondly, we can actually implement an observation function to turn this normal form back into any arrow, any generic CCA arrows. So this is like an interpretation of this data model. And you can interpret these two constructors just by mapping them to the corresponding arrow combinator, which will give you the arrow instance you would like to instantiate. And thirdly, there is implementation of this model as the arrow class, arrow loop class, and arrow init class. So this can be regarded as, if you are familiar with normalization by evaluation, the first step corresponds to the model, and the second step corresponds to the interpretation, and third step corresponds to the reunification of term level expression into the object level. And with this, we have implementation of the normal form, and we have a way to instantiate any of your generic arrows into CCNF, and then we can turn it back to give you back a generic arrow that's in the normal form. And furthermore, if we optimize the observe function, we can get the speed up we want it. And this is done by specializing observe to some concrete implementation. For this, we can use the SF arrow we saw just now, and we implement, basically we just use the SF, the corresponding arrow combinator for the SF arrow to implement observe. And furthermore, we can derive an optimized definition for observe SF, which is given by this loopd function, and which is defined as an SF over a transition function here. And thirdly, this is more critical point in this slides. We need to fuse observe with the context in which it's being used. So we fuse it with the sampling function, for example, the nth function sampling the nth element in the output of the when you run the arrow. So we just observe using SF and use nth SF and combine these two, we get the nth for the CCNF type. And this step 2 and step 3 has to be done by hand. So we have to hand optimize these definitions to give you the final optimized versions. And then we can run our program with a compiler and get the desirable speed up. So this is a performance comparison. We computed some number of samples for a set of programs. This set of programs, they are taken from our previous work, and we put in 2 more slightly bigger programs in sound synthesis, and we quantify their size by measuring how many states, how many local states they have, how many loop combinators they have in the source code. So you can see that these 2 programs, they're indeed a little bigger. And we compare the normalized program with the ratio with the normalized version. So CCNF is our dynamic normalization technique, and TH is template Haskell static normalization technique. We can see that for small benchmarks, they're roughly comparable. So indeed, this technique works at runtime. But for bigger size programs, there's still a gap here. So why it works? Why it didn't work like 6 or 7 years ago? First of all, unlike SF, which is a data type that's recursively defined, right? We can see here SF is used recursively. This CCNF type is not. So GHC is able to, optimize pure functions, even pure functions that's defined recursively in a reasonably give you reasonable result. But as soon as you introduce some data type in it, GHC seems to have some problem with its optimizing this kind of program. So using CCNF data type is important here. And also the hand optimized observe function is important to get performance, so that GHC knows, well, you're observing this normal form, and then we can compose them together and statically compile them into a fused result. So all that all that heavy lifting is actually done by the compiler, and indeed GHC has improved. If we run GHC 6.10, that was like 6 years ago, over the same program we have now, it still fails to optimize. So compilers help those who have compilers. If we guide our program to make use of the wonderful features in our compiler, we can indeed get performance. Therefore, in GHC we trust. Well, if we take a step back, there are several levels of abstraction here. At the higher level, we have type class and error loss. We write our program in the generic arrows. So this can be regarded as some kind of axiomatic semantics for our program, the error loss. And a level down, if we interpret this program using a concrete data type, like SF or CCNF, we give it an interpretation in a data type. This can be regarded as a denotational semantics. And if we tear down the data type, if we look inside the data type, what was captured in the data type in the case of a CCNF is actually a state and a state transition function that corresponds to a Mealy machine, which is an automata. And this can be regarded as operational semantics. So in a nice sense, this work connects the three levels together. And if we look at the observation function, the optimized observation function here, we use the transition function f to apply to the input, which is unit, and the current state, we get the next state and the next and current output. And the next state is being used recursively for the next step. I don't think I have time to go through these other slides. I just jump to here. So there are many related work representing arrow computation as data type. It's not new. It has been explored before. And there are also other ways to generalize arrow computation and make it easier to optimize by using special constructors for the routing kind of computation instead of leaving it just to the pure arrow. And deriving implementation by equational reasoning is also not new, and there's also been studied in using free representations as a kind of optimization technique. So in some sense, the normal form for arrows can be thought of as a free representation for the CCA. And there's more in the paper, and we have more details, including how we implement mutable states with ST-monad and proving that it's actually instance of CCA, and there are detailed performance analysis. And our code is available to download. With that, thank you for listening to the talk.
Okay, we have time for maybe 1 or 2 questions while Ivan sets up.
Hi, Joachim Breitner, Philadelphia. Besides template Haskell, there's another meta-programming mechanism in THC, which is rewrite rules. Have you tried implementing this using rewrite rules?
Yes, we have tried rewrite rules. They don't work as intended. So it's pretty hard to tune the rewrite rules at which optimization step, which level to kick it in, and all that. It's not as effective as we had thought. Actually, our implementation, if you look at the source code, there are some use of inline and some use of specialized. Those are the pragmas of GHC. But those are actually not required. If you remove that, they still work. We put it in because we want to have a fair comparison when we measure the benchmarks compare with the SF implementation and all that. Yeah, so maybe GHC rules will work as a normalization kind of implementation, but in our experience, it's not as well. It didn't work as well as a straight implementation.
All right, let's move on, and if you have more questions, just find Paul in the break.